Everybody doing all right today? Okay, I want to see how you're doing with synthesis. Okay, how can you go back here? I went back to the ketone. Basically, how can we get these groups on the ring, starting with benzene? You may come up with ways to put this on. I don't know that we know any way to directly put it on. We know precursor here is our ketone. I went back to the ketone. If I have that, I can remove the oxygen with Clemmensen reduction. Key will be posted upstairs. How do I make this? Well, that's a Friedel-Crafts, so I can go back to anisole. Do a Friedel-Crafts with anisole, ortho-para director. We can just get out the para and then do the Clemmensen reduction. How do you want to make anisole? You can take chlorobenzene, react it with this nucleophile. That's methoxide. What do we need? 300 degrees. What mechanism am I proposing here?
NAS.
The NAS requires a ortho or pair activating group. Does this have an ortho or pair activating group? No, can't do NAS here. It's going to be a benzyne mechanism, which we're doing right now. I don't think I finished it up. How do you put the chlorine on? I didn't show that, but basically benzene with what?
Cupric water.
Not cupric chloride. AlCl3 or FeCl3. Cupric chloride is an oxidant, not typically a Lewis acid. And so we can put the chlorine on. There's other ways to do this. Well, this is an ether. You could make this ether from the phenol. If you have the phenol, you treat it with base to remove the O, remove the H, make a minus, and then add methyl iodide, do SN2, oxygen attacks methyl, kicks off iodide, and you put your methyl on. How do you make phenols? Have we seen how to make a phenol on ring? Diazonium. So you can, I just did off this all together. How do we get to a diazonium? We nitrate, reduce the amine, react with nitrous acid, and then the diazonium is reacted with basically just water and heat. And we can replace the diazonium with an OH.
Is that all we would need to show in a mechanism is the 1, 2, 3, 4? We don't need to draw the diazonium.
Well, this is not a mechanism, this is synthesis. I just did it like this because there wasn't a lot of room. You can do it like this if you want. Problem with that is it limits me in giving partial credit because I can't see what you were thinking as much. But you guys should know that if we're going to do diazonium, what do we need? You got to get the amine. Well, how do you make the amine? You make it from the nitro. Well, how do you make the nitro? So you got to nitrate, you got to reduce it to the amine, then you do the diazonium with nitrous acid, and then what do you react the diazonium with? It's basically just H3O+. By the way, this up here, what does this mean when it says lab day, Wednesday, Thursday, Friday? You circle your lab day. So I come to lab on both days, so I circle both. Nobody comes Thursday, but that may be another semester. I know you guys are kind of quick to turn it over and start going, but please circle your lab day. I need to start doing that. Okay, how do we make, we got this side chain alkene. How do you put cyano on the ring? Diazonium. Okay. How do you want to make this from nothing over there at all? We looked at doing an elimination. We can go back to the benzoyl bromide. Because if I can go back to that, can you convert that to this? Yeah, do an E2 elimination. Eliminate it off. Well, how do you make this? From that, do NBS or bromine with light. Not a Lewis acid, but light or peroxide. That gives you a radical reaction. How do you get this on? Well, that comes from a ketone. And at this point, I realize we need much more room here. I gave enough room for one. We gotta be careful though. Because at this point, you got to be careful. I could have went back to this here and said, well, I can remove that to make this. Then how would you go back from here? You might go back and say, well, if I have this, I can come forward by doing Friedel Crafts. Will that reaction work? No, that reaction doesn't work. Why not? Oh, that's a Mattergrid 4 director. So you got to be aware of that. That's a common error that you guys make, is doing a reaction where you're either, it doesn't work because of meta directing, or maybe you do a reaction and this is a meta director and you do a reaction and you put something para. Because even if it did work, what type of director is this? Meta, it wouldn't go para. Mark?
Can you go back from the ketone on the last one we drew to NaCN? And then
what do you want to do?
so the ketone would be orthopara. So you can do NaS,
You want to react this with what?
NaCN.
Okay, let's look at that. That's going to react with this and put a C in here. By what mechanism?
NaS.
NAS. NAS involves displacing a traditional leaving group. There's no leaving group here. You're right, it is nucleophilic. I thought you were going to say this is EAS. Then I was going to tell you, well, this is not an electrophile. Cyanide, an anion is not an electrophile. That's a nucleophile. How can we put a, can we put a leaving group here? Can we brominate and go here?
Yeah.
No, it won't go there. It's a meta director. What if we brominate first? I mean, we can put that there and say, if I had this, could you react with that and get this? Yeah, that'd be an NAS. How do you want to make this? Do you want to take do you want to take that and brominate it? No. What if we take bromobenzene and acylate it? Will that work? Yes, because bromo is an orthopara director. We can say it goes para. How do you make bromobenzene? You should be able to do that. That's just benzene with bromine and rusty nail. There's other ways. I showed another way here. Please check the key. Basically, at this point, we get into there could be numerous ways. Any questions about the synthesis? This is not to be exhaustive discussion. I just wanted to get you thinking, going, challenge you. Okay? Please check the key. How are we doing? Yeah? This one's pretty straightforward. Everybody get that one? Will that react with KMNO4? No. First day of lecture we said no, it doesn't react. That doesn't either. What does it require? What's required for these types of compounds to react with KMNO4? Hydrogen on benzoyl carbon. Which one has that? That one. There's your answer. The reason I want to give you this is to illustrate that the reaction with KMO4 is also sort of used as a chemical test. Okay, it's a reaction, it's a synthesis, but it's a chemical test, and a number of you have seen that in the NMRs. Okay? So if you're told the compound does not react with KMnO4, then this cannot be the answer, because that does react with KMnO4. Since we're talking about NMRs, how are we doing on NMRs? Just like before, there's been several in the workbook to work. Any questions about the NMRs? Doing all right with them? Any questions about NMR? Okay, let's look down here. Chlorobenzene doesn't react, but chloropyridine does. 2-chloropyridine. I did a nucleophilic addition to give this. This is resonance stabilized. Boom, boom, boom. And then from there, I did an elimination using these arrows, electrons back in, reform pi bond, kick off the chlorine. That would give this. You have to go neutral. I used a second equivalent of ammonia to take the H to get product plus ammonium chloride. So I did an NAS. Questions about why NAS? How many mechanisms have we covered? 3. EAS, NAS, and we need to finish up benzyme. What is ammonia? An electrophile or nucleophile? It's a nucleophile, so you're not doing EAS. So what substitution mechanisms do you know using a nucleophile? NAS or benzyme? Okay? Now in the information it said that first off, chlorobenzene doesn't react. It also said that only one regioisomer is formed. Now we haven't quite got there yet. This is basically sort of leading us into reviewing this chemistry and leading us into what we're about to talk about. Questions about this mechanism? How do we do? What I'd like to hear is what stumped you up here. I mean, that's the only place they can go. I mean, nucleophile N, you move electrons onto... Okay. So, here's a quick Trey.
I don't know why I got this confused, but when I did it in the first step,
I had my lone pair on the top sigma bond over the NH3 and Cl, and it did resonance to the left.
Did you do something like this? What's the objective here? The objective is to replace the chlorine with the nucleophile. What mechanisms do you know to do that? Either NAS or benzyne. Now, I could see somebody trying to do a benzyne here. But benzyne typically requires harsh conditions. We're at room temperature. Okay, did you do benzyne? Okay, well another reason is once we finish up benzyne gives regioisomers. Okay, we haven't quite got there yet. This is an NAS. Question though, why does the NAS take place with this compound and not the one above? Matt?
Presence of the nitrogen beside it.
And the presence of nitrogen allows for what?
Allows you to do that extra resonance set, because you can use those electrons.
It's not necessarily extra, because without the carbon you'd also have it. But what is so special about that resonance structure? This is what we summarized. To do a nucleophilic addition, the anion has to essentially be put where? On an electronegative heteroatom. And there you go. It can be put there with pyridine. That electronegative heteroatom is built into the ring. Where here, the only way to get an electronegative heteroatom is to have one as a substituent. Okay? Let's look at, let's finish up benzyme chemistry. Also at the end, don't let me forget to pass back the lab for the Wednesday group. Okay, the Friday group, I'll give you the social lab this afternoon. Okay, we're looking at the Benzene mechanism. Before we get to the next page, let's look back here at our mechanism. We did the mechanism. I'm not going to redraw it. You have it. Here's the product. Did we show the product at the end of our mechanism? I don't know if I drew it or if I just drew a line to the... I drew an arrow up to that? Okay. We had here, so I'll just do that. Pretend all the rest is written there. Okay. We have to point something out. What's the purpose of this? Did we say what the purpose of that was?
No.
We did not. I showed you a mechanism for all of this, and I said, there it is. Well, I kind of lied to you. We have to do a little bit more. Is this reaction under basic or acidic conditions? Basic. Hydroxide's a base. How is this going to exist under basic conditions? Is that compound acidic or basic? Phenols have acidity. Okay? They're not as acidic as a carboxylic acid, but they're more acidic than alcohol. We know phenols will actually react with sodium hydroxide in a Williamson ether synthesis. This is going to react with hydroxide. I'm not going to show mechanism because I don't have a bond shown out there. Does everybody agree that that will react to give that plus water? You got hydroxide here. You cannot say, what's the pKa in a phenol? Carboxylic acid is about 5. Phenol is about 10. The last page in the workbook shows that. pKa about 10. What's the pKa of water? 16. Which side is favored, 10 or 16? 16. That side's favored. By how much? 10 to the 6. A million. You cannot say, hey, phenol, even though you're favored to do this with hydroxide, I don't want y'all to do that. It won't listen to you. That's going to happen. Because of that, you have to use, your hydroxide is consumed. Not only is this happening, but this is consumed. And so you need more over here to do that part. So actually, this requires 2 equivalents of hydroxide. One to do the main reaction, which we looked at last time, but it also requires hydroxide to do this. Now you might say, well, what if we only use 1 equivalent? That'll just do that, and we won't do that because it won't be enough. Well, it won't do that because as soon as you start making some of that, this will no longer react with this. It'll go over there and react with that. Because acid-base reactions are very easy and instantaneous.
So there's no H transfer?
Do what?
Because in the last class, you said there was an H transfer at the end. But H plus transfer.
Yeah, that's how we made that product. But that product I'm showing you then reacts with hydroxide, which is essentially another H transfer. All acid-base reactions are H plus transfers. Here's end step 1. That is really the end of step 1 that I did not tell you last time. Now somebody tell me what's the purpose of adding an acid? You got to put the H back on. That's why you have to work it up with acid. Because at the end of the reaction, it's in its basic form. Does this make sense? This is a practical consideration. Two equivalents are actually needed. Now, a long time ago, somebody made up some stupid analogy, okay? I don't know who it was, it might have been me, that if you knit a sweater in a pool, when you get through knitting it, it will be wet. Okay? And at that point, you have to then dry it. Okay? Now, this is so stupid, you're like, what in the world does that mean? Okay? And this evolved from something, okay. When you make a product, you have to say, okay, what conditions am I under? Because if you're in the pool, you're going to then have to dry it. You just can't say I'm done and hand me a wet product. This is under basic conditions. The product will exist in basic form. When you get through making it, you got to dry it up. You got to add some acid with the proton on. Okay? We saw that on the quiz we just took. But it was the opposite. It was, we had to add a base, actually. Why do we have to use 2 equivalents of ammonia? Because at the end of the reaction, I could have used Cl minus to take it and make the product plus HCl. But that's a base. It's going to react with HCl. If you look at your equilibrium, it'll stay here. You have to use another equivalent ammonia to remove the H and make it neutral. We have to make this neutral by adding an acid. Okay, I don't want to go on with that, but a lot of times you'll have a necessary workup step. Okay, did we look at Diels-Alder? When this mechanism was first proposed, a lot of people said, oh, that don't look too right, I don't believe this. Then people started saying, well, I've got some evidence. And somebody said, you know, hey, I formed a benzyne, and when I threw in a diene, it reacted to give this. That's very analogous to a Diels-Alder. And I'm showing you that I think this is formed. Look at this product that formed from it. Must have came from a triple bond. That's how we did have the double bond here. And that's a little bit of proof that this might have been actually what was there. And actually, reacting benzynes with dienes is very common. Here was a bigger experiment. I sent an email about this. Dr. Roberts he was at MIT, later moved to Caltech. He did an experiment where he reacted bromobenzene with a strong nucleophile. The carbon was labeled. Carbon was labeled as C13, the one that the bromine was on. He reacted it with potassium amide, that's K+, and ammonia, minus 33. Ammonia is a liquid at minus 33. So this is done basically using ammonia as a solvent. But this is a very strong nucleophile, your NH2 minus. Because actually NH3 neutral is a good nucleophile. NH2 minus is very strong. And this chemistry does work even at cold temperatures. Because if you remember on the previous page, it says you need harsh conditions or what? Or very strong nucleophile. So your NH2 minus is an example of a very strong nucleophile. They knew this reaction worked. But if you just do this reaction and it's not labeled, you just get aniline. And it looks like, well, maybe the amino just replaced the bromine, you got aniline. But he said, hold on. If I do it with labeled here, and that's labeled, and I do the reaction, I don't get the same product. I get some amine on that carbon, but I get some with the amine on the adjacent carbon. Again, if that was not labeled, that would be the same product, and you couldn't tell the difference. So this said, hey, it's not just a direct displacement of the bromine. Something else is going on. Now, we've already showed the mechanism for the benzyne. How does our mechanism account for this? This is a benzyne. The first step is, now I've got my pi bond drum here, so I'm going to put the H over here. The first step is this takes the H. I'm going to do it all at once. A lot of times you can do this all at once. It's okay either way you do it. And just eliminate it off, and you get the benzyne. I'm even going to call it E2. I'll put it in the quotations because it may not necessarily be a strict E2. Again, there's 2 or 3 different ways to get to this point. You can refer back to Winston. Here's our benzyne. Which carbon is still labeled? Alanine, right? What's the next step in our... We made ammonia. The next step is, by the way, that's called elimination. What's the next step of the benzyne? Addition. This adds to the carbon. But look at here, at this point the benzyne is sort of symmetrical. Which carbon do we add to? If that wasn't there, which carbon? It doesn't really matter. If it adds here, and these come over, we get minus we get this with that labeled. From there, what do we need to do to get this? It's not a hydride shift. It's an H plus transfer. That would give that product. Will somebody tell me how we get the other product? Instead of it attacking there, I know you don't have a different color pen, but I do. It adds here, and these move over there. What does that give? We now have in here minus over there, and that's the starting carbon, that's the C13. And then how do we get this product? Now, I wish I'd drawn the amine over here, but it's the same thing, just flipped around. How do we get that? H plus transfer. And then you have a product where you have a benzene ring, a labeled carbon, and next door is an amino. Labeled carbon, next door is an amino. So that's the same product. He showed that you get 50-50 of this almost. So you have to believe, hey, it's not just a direct displacement of the BR. Something else is going on. Does this lend more support to a benzyne mechanism? Well, it does, and that became a sort of a seminal experiment. I sent out sort of an email about it. He did this in like the early 1950s. Actually still alive. He's about 97 years old now. So that was it. So, thus, these are actually isomers up here. Okay, they're kind of isotope isomers. You can get isomers other ways. If you take, what is this, perchlorotoluene, react it with the same conditions, we actually get 2 products. We get para-aminotoluene, or we get meta-aminotoluene. How do we get 2 products? Well, it's the same idea. Show the benzyne that's formed first. Okay? Just show the benzyne. basically we eliminate HCl, a couple of different ways to show it, and we end up with benzene plus ammonia, because NH2. Then the ammonia can either add here or there. Okay, I'm not going to repeat it, but right, it can add either place. If it adds there, that's para to the methyl. If it adds here, that's meta to the methyl. And again, I got it from over there instead of over here. Does everybody see how isomers can be formed here? And so it's not just a direct displacement here, and you say, hey, I'm going to replace this with a mean and get it here. Go back to NAS. NAS mechanism does not give isomers, because the NAS attacks the carbon where the leaving group is, and that's where it ends up. But benzene gives isomers because the benzene can be attacked at either carbon. Let's finish this up, just a little miscellaneous. Benzene chemistry can be done sort of sequentially. We treat this with N-butyllithium, which is what type of reactivity? That's a good base. The only thing you can do is your elimination to get benzene. You can't do NAS here. We're certainly not doing EAS because this is not an electrophile. Make benzene plus what? Plus what? Well, there's lithium here. You would make lithium chloride plus what else? Butane. Now here there's really no good nucleophile. That's not going to be a nucleophile there, like the ammonia ended up being. So you can make this and then use it for other things. Maybe you do a Diels-Alder. Here's something new. What if we then come in with a Grignard? What type of reactivity do we have here? This is essentially a methyl anion. Good nucleophile. Could that react with this? Which carbon do you want to react with, or are they the same in this case? Same. Here, here. And so I get methyl, and what is now here? Anion. Now you might could do a proton transfer, but this doesn't need to lose a proton. So this is not going to immediately transfer. What's the next reagent? What if we then throw in this? What type of reactivity do we have here? And so we put the alpha group on. That is illustrating very sequential, stepwise chemistry that can be done. Did that chemistry make sense that we just did? And in advanced organic, there's so much that's done like this. I'm just giving you a little flavor of it. Okay? Okay, we're out of time. That's it right there. Boom, we're done. Okay. So test on Monday. Has to be on Monday because I'm not going to be here. Someone's going to get the test for me. Okay? No, then there will be nothing to do on Monday. The reason I'm not here on Monday is so somebody can just come and give the test. Similar format, multiple choice, predict the product. There will be synthesis. Plenty of other synthesis in the workbook. A number of you have been asking about the handout synthesis. Will be a comparable to spec problem, and there will be mechanisms. Very similar format. Cheryl? Nomenclature, yeah, we did nomenclature of aromatic compounds, including there was about 7 common compounds that we know. No. Andy? What? Lab for Wednesday. Pick it up on the way out. If you have questions, guys, after class, we can maybe, if you have anything important right here, or come by. Please yell if you're here. Vidya? Ariel? Sarah Oster? Ricky Bennett? Brianna Walton? Asma? Jason? Here. Karen? Matt? Mama? Sarah Ray? Precious? Camille? Sean Morgan? Andres? John? Trey? Kate? Morgan? Morgan? What did you,
Still Monday.
Monday. Sure. Sorry. Yeah, I got the dance.
I was always thinking about Amanda. I'm always calling you Chicago.
Yeah, I always call you Southern Illinois, Kentucky person.
Yes. Everybody should know that.
Excuse me.
everybody does something.
We'll